Today we're going to discuss how to compute and plot triangles, like the pictures you see above. So 2 weeks ago I presented a detailed proof of the following identity. Sine of alpha plus beta is equal to sine alpha cosine beta plus sine beta cosine alpha. It was a good proof, by the way. As part of the proof, I included some pictures of triangles, some very nice looking pictures. So here's the first picture. The triangle is sides A, B, and C. A is to the left, B is to the right, C is the base, H is the altitude, V is another altitude that goes from the origin to the extension of B. And here's another plot, A, B, and C the same, but this time the altitude H is off to the right, and there's an extension of C to meet that H. Then V is down to below the baseline, and there's an extension of B to meet V. So how does one create plots of triangles like these? Clarification, it's really just a single plot of a single triangle with different parameters. So there are two parts to this question. How would you go about computing the necessary information to make the plot? And then the second thing is, how would you use that information to create the plot? So the answer to one is general. It's applicable to any plotting software. But the answer to two depends on how you are going to plot, what software you're using. We're going to use Excel because that's what we're doing. And it might not be the best for doing this, but it actually does a fine job. But, you could say, well, I could do a better job with something else, and that's fine. Most of what we are going to do today is applicable to anything. So to refresh your memory, the triangle has a left side A, a right side B, baseline C, an altitude H that goes down to the baseline A, another altitude V that goes from the vertex off to the right. Okay, now in this version you have A, B, and C. You have the extension C prime that matches H, and the extension B prime that extends to V. So the plot is made of 7 line segments, a left side, a right side, a base. Then there are 2 altitudes, H and V. And then there are 2 extensions that are not always needed. The extension C prime and the extension B prime if necessary. So computing the triangle, for each line segment, there are 4 pieces of information that determine it. There's the XY components of the starting point. That's points 1 and 2. And then 3 and 4 are the XY components of the ending point. For each line segment, the starting point is either the origin or the ending point of some other line segment. XY components can be computed via the length and the angle. So computing the triangle, extensions are more confusing because they vary based on the scenario. And we'll look at the 4 scenarios. Scenario 1, Angle beta, which is the left angle, could be obtuse or right. Scenario 2, angle alpha is obtuse. Scenario 3, the angle alpha is right. And then scenario 4, angle beta is acute and angle alpha is also acute. It's possible to split scenario 4 into 2 sub-scenarios based on whether the angle gamma is obtuse or not, but in my opinion this isn't necessary, but I'll talk about it a little bit in a moment. So let's look at the scenarios in detail and see how you could compute the extension. So this is scenario 1. We have an extension C prime that goes off to the left because H is in the negative region. And then we have no extension for B. So there's no necessity to extend anything, so it'll be a zero vector. It starts and ends at the apex. In this scenario, this is like base case 2, C prime starts at the right vertex and goes to the right to meet H. B prime starts at the right vertex and it goes down to meet V. Now this scenario with a right angle, C prime is not needed. And therefore it starts and ends at the right vertex. B prime similarly is not needed. It starts and ends at the right vertex. So, and this scenario is just kind of confusing because, as you can see, V just corresponds with C completely, can't even see it. Yeah. Similarly, H corresponds with B. Okay, and this is like base case 1. In this case, C prime is just not needed. There's no extension necessary for C. As for B prime, it starts at the apex and it goes off to the right at an angle alpha. Off to the left by an angle alpha, I'm sorry. Now, scenario 4b, angle beta is acute, angle alpha is acute, but the angle gamma, it's also acute. C prime's not needed in this case. B prime, there is an extension and it goes off to the left again. But arguably it's not needed here because if you look at that, the V vector hits the base. There's no ambiguity there, but I still think it looks better to extend B because it helps the eye see the perpendicularity in this case. But that's a judgment call. You know, you could say, oh, I don't really want it there in this scenario. But then you would have to program it differently. So this is a sort of a cheat sheet to guide you in the various scenarios. And I won't go through it because this is exactly the information we just went through. So exercise 1, you're given angle alpha and beta, and they should make sense. They should sum to less than 180. And a length, side length A, it's got to be positive. You have to compute the xy components of starting and ending points of the 7 vectors, the 3 sides, A, B, and C, the 2 altitudes, H and V, and the 2 extensions, C prime and B prime. So let's go to the spreadsheet and see how you would do this. All right, so alpha and beta could be anything. We'll just put in values there. A can be anything. We'll make it 1. Gamma is computed. It's 180 minus alpha minus beta. Delta is the complement of alpha. And then we're going to convert the degrees into radians so that we can use our trig formulas. So B is A sine beta divided by sine of alpha. That comes from the law of sines. C is A sine gamma divided by sine of alpha. All right, H is A times the sine of beta. It also could be B times the sine of alpha. It better be the same value. It's good to check your work. A is AX is the X component, and AY is the Y component of A. So the vector V is 2 ways of calculating. It's A times the sine of gamma, or it could be C times the sine of alpha. Again, it better be the same either way. The X and Y components, you use the angle delta to calculate those. By, that is an intercept term. Now, when the angle alpha is 90, there is no intercept, so we have to set it equal to 0. Otherwise, it is C times tangent of alpha. All right, now let's put in the apex there. That's the AX and AY terms there. Then we have to put in the right vertex. That's the distance C, and in the X component, and the Y component is 0. The y-axis, the X component is 0, and the y-intercept is that number we computed there, by. Okay, so several of these vectors start at the origin. B starts at the apex. H also starts at the apex. And it goes straight down. A starts at the origin and ends at the apex. B starts at the apex and goes to the right vertex. C also goes to the right vertex. H goes straight down, so it has the same X component, but the Y component is 0. V is the Vx, Vy numbers we computed above. All right, now we're ready to look at C prime and B prime. We'll first compute this thing called template. It'll be just a logic that allow us to navigate this 4 scenarios. So if beta is greater than 90, then that greater than or equal to 90, that's scenario 1. If alpha is greater than 90, that's scenario 2. If alpha equals 90, that's scenario 3. None of the above, which is 1 there, is scenario 4. Okay, I'm putting the dollar signs in there to make sure I can copy this over. Now I'm checking to see my work to see if I put in different angles, do I get different scenarios. So I checked 1, now I'm checking 2, 3, yeah. All of these scenarios are checking out. Okay, so the logic here, 1 and 4 start at the origin, and then scenarios 2 and 3 start at the right vertex, which is P17 there. Okay, the y value is always 0. That also is 0. Okay, so in this case, the scenario 4 starts and ends at the vertex. Scenarios 1 and 2 end at the x component of the apex, and scenario 3 starts at the right vertex, ends at the right vertex, I should say. So B prime, 1 and 4 start at the apex, so, and the apex is O17 here. And then 2 and 3 start at the right vertex, which is P17. Now, if I did everything right and I copy this cell down, I'll have the right values for Y as well. Okay, now, scenarios 1 is the apex. Scenario 3 is the right vertex, which is P19, and then scenarios 2 and 4 are the y-axis, which is Q19. Okay, so let's see if we did it right and we copy it down, we'll get the y values as well. All right, so let's put in some different values here and see if it looks like it's computing correctly. Okay, scenario 1, I'm getting a C prime. That's what I'm expecting. If I change it to 90, I won't get any extensions. Okay, and I don't see an extension there. It starts and ends at the same spot. Okay, if I change alpha to 110, then I will get an extension of C to the right, which I do. And B prime will extend down, and yes, it does. Okay, let's do 90. I will get no extensions here. Okay, that's right. I'm getting no extensions. And then let's try 50. No extension for C prime. B will extend to the left up to, yeah, it works. Okay, plotting depends on the software, but the idea is similar. You parameterize x and y. Y is defined by f of x. But for line segments, it's even easier. You just use the same parameter for both x and y. So, for example, let lambda be a parameter between 0 and 1. The vector v is the convex combination of points A to B. So what does that mean? The x component of A, it's a convex combination of the x components, and then the y is the convex combination of the y components of A and B. So let's go to the spreadsheet and you'll see how this works. So we'll just do one parameter. We'll do A. We'll see what happens when we, let's see, we'll plot A as a function of the lambda, and x, both the x component and the y component. So lambda starts at 0, and we will step it by 1 over 100. We could step it by more, or less. It doesn't matter too much, just as long as you have enough data. 100 data points is fine. So we calculate the value of x as the x1 component times 1 minus lambda times the x2 component times lambda. Now we're going to copy the formula over to the right, and we're going to change 17 to 18 and 19 to 20, and that way we'll pick up the y values. We'll just bring that down to row number 124. That's 100 values, 101 if you count, each endpoint. Okay, and then we're going to plot A with a scatter plot, and that's what it looks like. It's not formatted correctly, so I'll show you how to change the format. So let's just do this again. We're going to select that region. We're going to hit scatter plot, and all right, let's see. Let's change the angle to 60. All right. Now we're going to format the data series as a solid line. I'm going to change the color so it's a little nicer. Marker. I don't want a marker, so say none. Okay. And the grids, I have to have a square grid, so I have to override the values that are put in by Excel. Just a second, that should have been minus 0.5. I'm going to go from minus 0.5 to 2. And I'm going to do the same thing for the left axis. It's going to go from minus 5 to 2. Oh, it's important to override that, make that 0.5. I'm going to put the labels low. I'm also going to make those labels low. Oh wait, that should have been 0.5, and make that low. Okay, now I got to square this up. So those grids are not square. I got to manually change it to make it look more square. It's pretty good. Maybe I could have made it more square, but it's good enough. Change the angle. Yeah, it's computing a new vector. Excuse me. So exercise 2, plot all 7 vectors of exercise 1 in a single scatter plot. So 3 sides, the 2 altitudes, the 2 extensions. So we already got the data. All we have to do is kind of duplicate what we did in that one for A. Now, I kind of already did it. So what I did was I made lambda loop. So what it does is that every time I get to 1, it starts at 0 again. Okay. And then I created a counter. Every time I get a 0, I increment the counter so I know what line segment I'm on. And then another thing I did was I put the data off to the right here. And the reason why is because it'll make it easier to copy as I go down. In fact, why don't I do that? Why don't I copy some data? So here, I'm copying that one. And then when I go down, I'll just shift it 1 and copy it. And then it would make exactly the data I want for the next line segment. And then I copy it down and I'm getting the data for the line segment. Now the X in the X column, what I do is I simply sum up all the data that's off to the right. So see that sum? Yeah, it's just summing up a bunch of data to the right. That way I don't miss anything. Now let's look at the very last value. At 730, K730. K730, that's the last data point. So I put in K730. Okay, that was it. I mean, basically, that's the exercise is done. I've got all the 7 line segments there. I just have to format it. Now, I changed the color. And I also changed the style of the line segment to be dots when it's an extension. That one, I want to change the color. Okay, so now the color matches, and I changed that to dots. Made it a little bit wider. Okay, maybe make that a little thinner. That a little thinner, and yeah, that looks pretty good. Let's change the value and see if it computes it correctly. Okay, I'm cutting off something. Let's scale it down, change the scale factor. Yeah, that looks good. That's what we wanted to do. Okay, time to close the spreadsheet. Thank you.